what's its fit, form, and function. So that is another major thing. So I know, okay, this part is performing this way, it fits to this, and it needs to function this way.
You kind of have to work backwards, right? Like what the end product is, and then how everything clicks together.
Yeah.
What's the easiest way to make it, and now draw it, right?
Yeah. Mm-hmm. The ASME standard for tolerance is based on fit, form, and function, which is geometric dimension and tolerance, which is different than plus or minus, but plus or minus still you need to understand fit, form, and function. So. Well, my name's Trevor Reaves. From Florenton, Alabama. I went to school for mechanical engineering at University of Alabama, Birmingham. A lot of the schooling was a lot of theory. I learned SolidWorks there, a few different CAD programs. After college, I started at Hyundai, stayed there for about a year as a process engineer working on the line, so that kind of brought me into the manufacturing space a little bit. After that, and due to a long drive I was making, I decided to move to this manufacturer, and the first day there actually the day of my interview, they took me on a tour of the place, and that was the first time I ever saw a lane chart deck. Saw the LS2s and LS3s. So I started as the manufacturing engineer there, and that's where I kind of got this, I don't know what you call it, a bite maybe, of like, man, I really like the manufacturing space, machining. I love taking something from the computer or a hand-drawn sketch, from idea to here it is in real life, how it works. I love working through the issues that you'll find doing that, so because there's a lot of them. And probably 2 months ago, I think, I met with Nick and Travis, and I took Nick probably 6 hours, and I just kind of showed him, the basics of SolidWorks. Just walking through how I design stuff, some tolerance and stuff I put on drawings, just stuff I've kind of learned over the past few years. So that kind of, I think, helped them speed up their process. So now Nick's on his own and he's doing very well. So doing great. My company is Reaves Consulting LLC, so it's a general name. So I do several different things, but I mainly offer drafting services. So SolidWorks, AutoCAD. I can do both of them. I can do CATIA. I don't have it in-house, but if there's a customer out there that needs CATIA help, I'm capable. And I am a CWI, so for D1.1, so I can visually inspect welds. So I do offer that as well. I don't have a website currently, but you can reach me at the email. I can give you my email, and then I'll give you my phone number as well. So, yeah.
My name's Nick Phoenix. I work at Lane Chart. I met Travis in 2017 after we had the company that I was working for at the time purchased a LS2, one of the early model lane sharks. We kind of hit it off and slowly freelanced with him on and off for a few years. And as they kept growing, I think it just became where they needed somebody more in-house, and they had somebody for that at that time. And then didn't hear from him for a couple of years, and out of the blue got a phone call at the exact right time in life, and it worked out. So here we are. And as I came on, it was primarily for internal IT support to make sure that the business systems were operating correctly. And with this little lingering hope and dream that I could move into the more manufacturing drawings and using the 3D visualization stuff. And finally the opportunity arose and started kind of just poking around. We had a SolidWorks license, but I was super intimidated by it because it was different, completely different from what I'm used to, which is 3ds Max, primarily used in movies, games, and just more visual stuff, not technical. And then as we started talking more, I think at one point Travis said, learn it. Just straight up, just do it. So I said, can I reach out to Trevor, which was definitely a turning point, because getting insight from Trevor on this allowed me to kind of see the real world application rather than just watching YouTube videos, which was a good way to get the basics, like where to click, but in reality of tolerances and materials, just mating things and making sure everything works correctly, and actually seeing the product that he worked on for Lane Chart and then being able to get his like one-on-one help, put everything over the top. So that was the push that was needed. And since then, which has only been a few months, just learning a lot and moving forward as Travis comes in with lots of changes and updates. It's always exciting to hear new ideas and kind of think about the future. So.
Basically, whenever I first started, I would just draw stuff out. Like when I first started, I was driving back and forth between here and South Carolina a lot. So I designed a lot of it in my head. And then when I get home, I would sketch stuff up. And so I would make sketches, and then I would come actually right next door to where we are now, to Mr. Keller's, and I would sit down with Scott, and he would design everything on their plasma table. So it's just flat drawings on there, and we would draw everything out, and then they would cut it, break it for me, and then I'd go to my dad's, we would weld everything up, and it was basically just trial and error for however long that took. From day one, I wanted to be able to do all this in-house, because anytime I would want to try a new idea, I would have to sketch it out, cut it out, or just build the whole piece myself, assemble it, and figure out if it would work or not. And a lot of times it would just not work. Luckily, Nick came to work for us 21?
Yes.
20. So backstory on Nick, if you haven't watched the podcast, Nick bought a unit in 2017 because he worked for a place that really needed one. Nick and I hit it off, became friends, and he actually designed the first 3D model for us, which was really he just did it out of the kindness of his own heart, I guess you'd say. He was just bored, wanted to do something cool. So that's where our first real 3D design came from. And then fast forward back to 21, he comes to work for us doing IT, and I'm constantly wanting to change stuff. And Nick is constantly wanting to do more, which is a great combination. So back this time last year, I think, is whenever we decided finally, all right, I've had enough with not having all of this under my own roof. So he and I went to FabTech last year, went up there with the intention of buying cobot robots to weld everything, and spent 2.5 days looking at all those, and then finally realized this isn't going to work, and we switched gears to looking at industrial robots. We found what we liked. We spent, I don't know, 3 or 4 hours in the hotel room talking through all the problems, trying to figure out what was the best solution. Went back the next day, talked to the OTC guys, which is the robot that we ended up buying. And so in all of that process, Nick has just slowly began learning CAD. Is it SolidWorks that we use?
SolidWorks.
Yeah, so doing all the SolidWorks stuff. And so now we have the ability to do any changes that we need in-house.
All right, so right now what we're looking at is a SolidWorks assembly file. So lots of smaller components making up the full, pretty much the finished product, with a back plate and a swing arm. And this fixture itself can actually hold 2 swing arms and 2 different back plates, and then 4 hammerhead pivot arms. This specific fixture is going to be universal across hammerheads, LS3s, and LS4s. So it'll make the manufacturing process a lot smoother. So essentially, if there's a change that needs to be made, Travis typically he has these flat drawing sets. So this section of that is what we're seeing on the screen here, to hold swing arms. If he looks at this or one of the 3D files and says, well, this isn't going to quite work, or I want to make a change that would help speed up the manufacturing process, let's modify something. So he'll red mark this, bring it up, we'll open the file together, and then we can start picking things apart in SolidWorks to produce a new drawing set. So for example, if this sub-assembly of the hammerhead pivot point arms needs to be modified, we could open up just that part and start to figure out what component of this, or, you know, as we were talking about tab and slotting, if one of the welders runs into an issue with one of the tabs and slots or needs to be shallower or deeper, this is where we'd make that change before going back to the 2D drawing sets.
And what's cool is you can actually import the part onto this. So the pivot arms that this is holding, we have those designed. So you just import those, set them on there, and it'll tell you if something's out of whack or something won't fit.
Right.
And so you just make the adjustments, and you're good to go.
And then this is an example of tolerance right here.
So you can explain that we tab and slot everything and why the tolerance is important in that aspect.
Why they are the way they are.
Yeah.
Okay. So tolerance, and it's hard to describe in a short sentence. So I'm gonna try my best. But there's plus and minus tolerancing. There's GD&T. So when we talk about tolerancing, if we have a hole and a pin, so the pin's got to go in the hole. How large can that pin be when we have the smallest hole? So if the pin's 1 inch and the hole is 1.005, which is 5/1000ths of an inch over, the pin's going to fit. But if the pin is 1.01, it's not going to fit into the hole. So that's what we mean by tolerance. So tolerance, you want your parts to fit together correctly. So you need to put a number on that dimension. So if you have a 1 inch pin, you need to put plus or minus, whatever you need to have based on where that part is mating to. So it's kind of something you learn over time. There's an issue with tolerance stack up, especially with plus or minusing. All the lane sharp stuff is just plus and minus tolerancing. Where GD&T, which is geometric dimensioning and tolerancing, that helps a lot with stack up. It's not really a new way of tolerancing, but everybody's starting to move over to that.
Can you give us an example of
GD&T?
the tolerance stack up? I've never heard that term.
When you have multiple parts that fit together, and you have tolerancing on each of those parts,
I get it.
you will have a stack up of those tolerances. And sometimes you'll run into issues like, well, these parts are right based on the drawing of the piece part, but when I put them in the assembly drawing or the assembly itself in real life, they don't fit together. What's happening is because the tolerances are stacking up. So you get that a lot in plus or minus tolerancing. GD&T helps with that a lot. You want your pin to fit in your hole. How big can the hole be? How small can the hole be? How big can the pin be? How small can the pin be? So there's actually a machinist handbook that there's tables that tell you, your tolerancing values. So it's there to help. But, if you have something that's being machined, that's what your machinist needs to know. What are they going to shoot for? If you give them, they want to make a 1 inch pin on a lathe, what are they going to shoot for? 1 inch? How small can it be? Can it be under 1 inch? You need to tell them. So usually what happens is if you give them a 1 inch pin, you do plus or minus, say, 5/1000ths. So it can be 1.005 or 0.995 size. So usually they'll shoot for 1 inch. They shoot for the average. So they have play back and forth. So that's tolerancing in a nutshell.
The way we originally built it, it was a flat deck with one hole, and we would measure off the corners of everything, get it lined up, make sure it was straight, and then tack it in. Okay, go to the next part, make sure it's sitting right, and tack it in. So there's so much opportunity for error. Versus now, almost everything that goes on that deck, except for the angle iron on the bottom skids, has some sort of tab and slot or locate hole. That way you don't ever have to pick up a tape measure or a square when you're putting one of these decks together. That everything clicks in because it's all been laser cut. And so that's for the tolerance, like on the hole for the slot. If it's too small, the piece that clicks into it just won't fit. And so these guys take care of all that before it ever gets to me, essentially.
And your manufacturing method sometimes will affect what you need to put on the tolerances. So like when he's talking about tapping the slotted part, so if it's just a flat plate and you have a slot here, how wide your slot needs to be, say it's 2 inches by 2 inches. If you're getting it cut with a laser, you can put plus or minus 0.005 because it can hold that. Now, if you're doing it with a plasma, most plasmas, unless they're newer, I haven't seen one yet or worked with one at least, they're not going to be able to hold that. They're going to have nowhere near as a clean cut as a laser is. So your manufacturing method matters a lot. Now, you could get that plate machined on a mill, but it's not cost effective. It can hold even tighter tolerances, plus or minus 0.005, but you don't need that here, and it's not cost effective. So the manufacturing method definitely plays a part.
Yeah.
So there's a lot of different things that play into it.
Yeah, going from a plasma cutter to a laser is night, because with a plasma cutter, it's when it cuts, say it's cut through material, when it cuts, it does not cut perfectly straight down. It has what they call kerf. So when it's blowing through that metal, it will go one way or the other. So that slot will be angled in or angled out. And so if you have too tight of tolerances, that kerf is going to close that hole up and it's not going to fit in.
Yeah.
That's
and
one.
Your plate, if you put together 2 plates like this, or a T-joint, it'll start to wobble like that. Then your welder has to worry about is it square. If it's tighter fit, then they can just stick it in there, tack it, and be done.
But yeah, like as far as tolerance, talking about the DOM tubing that's on the end of the arm having to sit over top that piece.
Right.
Like you got to make sure that you got the right tolerance on that for it to actually sit down on there and not wobble and shake and move.
And since these were laser cut, I've been using your rule of the 5, 7. I didn't never say it. Of that.
And sometimes material comes into play too, like over the years of you using this, if you want a harder material, because if not, you have to replace that piece because it'll get worn down if it rubs a lot. So that's one thing to take into account as well.
Yeah, even with the laser cutting, I was shocked at how much the reinforcement lead warped.
Mm-hmm.
So when we build it in CAD, it's, to us, there's no variables in the real world like warpage.
Right.
So we're like, oh, it only needs 1 clamp. In reality, you need 5.
Yeah, when you get that thicker material, especially when it's thin cut on thick material, it gets hot and it wants to warp.
And going to water cutting would help resolve that issue.
Yeah,
but jetting is way more expensive.
Yeah,
so
it is.
it's in your problem solving with manufacturing, trying to find that balance of cost to efficiency to what makes the most sense.
But yeah, like the whole point of us doing these fixtures is 1, so we can put all different pieces on it, but 2, the amount of room that we've given ourselves for the robot to reach. Because right now, it can easily do the face of it on the current fixture, but then the back side of it, I have to rotate the trunnion at like a negative 45 degrees, and the robot comes in, and it's like snaking around a maze to get to a certain point, and it just takes a lot of time, and there's just too many chances for collisions. Versus this, it's a lot more open. Oh, and also with the old ones, there's places that we can't reach at all, so then that's when my dad comes into play, having to go and hit those spots that the robot can't reach because of the fixtures. So that just adds wasted time. Something that would have taken the robot 20 seconds to do, if it could have reached, it takes my dad an extra 30 minutes, maybe not 30 minutes, but you add up all those pieces and it takes my dad an hour to do one backplate from the robot to ready to go to powder coat, because there's parts you have to go in and weld and then clean up just to spatter, because we don't want spatter, we want it to be nice and smooth. So it's just a lot of wasted time, and this process of us designing our own fixtures will solve a lot of that. I would think by the time we get done with this, my dad's hour will be cut down to 10 minutes, 15 at the most. So I mean, he'd be able to do 4 times as much stuff. All right, so now we're gonna go to the shop and show some of this stuff in real life.
Julie,
Yep. You're famous.
Don't you do that to me?
What's up, Hydro boys? What's going on?
Is that the name of the band?
You having a good day, Jackson?
Yep.
Friday? Pretty cool.
Ain't she pretty? More bits.
Thing one.
Up electronic.
Can you hear me pretty good? So right here is the perfect example of why we're doing our own fixtures. So this one was designed it was designed to have two decks side by side, weld everything, flip upside down, weld everything. But the way this pattern works, it was just, I'm gonna say it was impossible, but I'm also gonna say that really it's due to my skill level. I could not get into all of the pieces on the bottom of the deck to weld them. So what I did is I basically butchered this one and made it so we weld the top, flip it over, and weld the bottom. Now with our new fixture, everything, we'll have two decks sitting side by side, and we'll have the room to reach underneath and get to everything. And it took me probably fighting with 20 different decks, or 20 decks in the process, to finally just say screw it, and I butchered this one and turned it into what it is. But you can see it's all held in the spot. We got the clamp, but it comes in and welds everything. And so you can weld, basically right now we can weld one hammerhead an hour when the robot's running full speed. The LS3 and the LS4 will take less time, so we should no longer have any back order issues. Unless I just screw up and don't order something ahead of time. Or if Landon over there screws up the robot. We got, to the other side, you can get a little better view of the.
You can go ahead.
So right now it's doing the top of the deck to the face of the the face of the back plate. And basically these programs run side by side. So we try to mirror each program. And here in a minute, once it finishes this, the trunnion will rotate and it'll do a different position. So it can move, this thing can move 360 degrees, and you can try to get to everything as long as the fixture itself isn't in the way. So, I mean, I've spent months trying to program this thing because it took me a long time to learn it. But the first time that you actually get to hit play and watch it weld these things, you can't describe the feeling. It's just really cool. So we're very excited about this part of our journey. You write the program for this robot, and then you bring them into their own program, which has the trunnion, robot 1, robot 2. And so you'll tell them to start and then you put what's called a fork weight, which basically, that way the trunnion can't move until both robots are done welding. Because inevitably, one will finish before the other. Just because it's on the, well, for me, it's impossible to get the program exactly mirrored between both robots. Like your air movements may take a little longer on one than the other, but this one will probably finish, 15 seconds before the other one, vice versa. And so it goes back into the home position, and it waits for that one. It gets to the home position, then it tells the trunnion to rotate. Once it stops its rotation, then both robots dive back in and start welding.
I was just going to show basically from the flat drawing, there's a part here, to laser cut product that's ready to be tapped, slotted, and tacked. This part will be right here to hold part of the swing arm.
Yeah, so this is, I guess, 3 weeks ago when we started on that picture.
Yeah.
So yeah, 3 weeks ago we started the process of the design, and we took 2 weeks of working on it and staring at it, thinking through the problem, sent it to Thin Cut Thin. We're not sponsored by them or anything. I just think they're a really good company. Just have fire to be something like that. So we just upload the stuff to them, and a week later we get this box full of parts, and I mean it's very well packed. They sent candy in the box with like a little thing, so I mean it's just kind of cool. So if you ever need parts cut, like they're seem to be a great company to work for or work with. Yeah, they have 4 or 5 other pieces over there that were too long that they couldn't process. I think they have size limitations based on the ability to ship it. Because we have pieces over there that are 10 foot long that they couldn't do. So I cut them here and took them to my machine shop and had them actually machine everything in it. But luckily we had the ability to do that. I have a wonderful machine shop that does all of our parts. Basically from almost day one, they've been doing our machining. It's called performance machining, and Earl and Jake that work there. Jake is the owner. Earl, I think is I don't know what his official title is, but he's the one I always bother. Great people to work with. I go up there all the time with ideas, and they help me with the process on the machining part. So like our hub, our shaft, our pins that we have specially made, just anything that requires machining that can't be laser cut, they do for us. And some of the great people to work with. We've been very fortunate to find good people to work with. Basically, we started from this idea of having the 2 back plates side by side like this, and then removing all the shit that's not necessary. Mm-hmm. So, like you can see, like there's all of this stuff here that you can't really get the robot inside here or down in here because you got you have a little bit of space under here. So what we've done is we're starting from this area and building up off of that with the posts essentially that will hold the back plate. Because the way this fixture is set up, it holds it here, 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 all the way down the bottom, all the way down that side, and then right there. So the way we're designing it for the new ones, is we're putting locate holes in the back plates and the deck, so it will locate off of those holes that have been laser cut. So it'll hold those pieces, and then all this unnecessary stuff is not there because it's not needed. Due to my inexperience, I don't like using the fixture to hold everything. I like to tack everything, set it on the fixture, and weld it. Like these were really designed to put all the parts in untacked and welded. So that's like this was a clamp that held this piece. This was a clamp that held this piece. there was another giant clamp here that held this, and if I was a better robot programmer, I probably could have worked around all that and it'd been fine. But it still didn't solve the problem of making the fixtures universal. So we still would have only been able to do a hammerhead deck or hammerhead backplate on this fixture. And we would have had to have a whole different fixture to do the LS3, a whole different one to do the LS4. So, number one, we're getting rid of all the unnecessary stuff that's in our way. And number two, we're making it universal. So all we do is change the program number to run LS3s or LS4s, versus the other way, we would have to take this fixture completely off. And every time you take this fixture off and put it back on, you have to go back through the whole program and make sure everything is right. Because as tight as the tolerances are on all those holes, one little tweak can throw, say if it tweaks a little bit over here, it can throw everything on this program off and the robot wouldn't weld it right. Because that robot don't know or care where the stuff is. It just knows where it was told to go and to start the arc and finish the arc. So all of that has to be exactly in the same spot every single time. Because if it's not, it messes up the stuff, and then that makes Dad spend a lot more time on cleanup, right? Which is wasteful time.
And so, how did you approach this whole process? Like,
I mean, the approach was kind of simple. It's just to make as many universal parts as possible, and then make the fixture as easy as possible to load, unload, and allow enough space for the robots for the programming.
does being here and being able to see how this works and everything help you when you're in the programming?
Yeah. Oh yeah, definitely. Because again, seeing it from a concept to a digital drawing and CAD drawing to in person, each step is so completely different. Having hands-on experience or coming into the shop and actually talking to Travis as he's programming, saying, all right, how can we improve this? And then what Landon's job is as far as uploading and monitoring the whole cell. I think led to some decisions that maybe would have been overlooked if I was in an office 1,000 miles away.
Yeah. And do you primarily have to do remote work, or do you get to see all
I've
of
been
these?
visited a few times, but primarily I do remote work. Other customers, if I have them, I'll visit if needed. So
Yeah.
it just depends.
Okay.
Kind of how it's worked with Trevor is I take the drawings, I mark them up, all of the big picture stuff. He does the adjustments, sends it to me, and then usually whenever it gets down to kind of like the last fine tuning, I've asked him to come visit us here. That way we can sit down and be in the same space and we can look at everything very, very specifically. And usually after that, we roll with it. So it's doing it remote is good for overall, but to get it perfect, for me, I like to have the person here. And that's one of the great things about now that Nick is taking it over, is at any point in the day, I can run into the office over there, go upstairs, sit down with Nick, and he just swings around to the CAD, the computer, and we go to work. So it's just the speed. It changes everything, being able to go from right here to right there, make the change, implement it, versus the way we've had to do it in the past is phone call, email, schedule a time, drive up there, sit down, go over it, come back to the office, they do the drawings, they send them to you, then we have to schedule another time, and it's a cumbersome process. It's like working for the government at that point. It's just not fun. So hopefully we'll iron out every issue we have and then create more and then iron those out and continue the process. We have it split. I guess those are new pieces, not split. We go all the way down. So yeah, this is another thing like that Nick and I designed from scratch. So I think I have forgot to mention, so our powder coating is not done in-house either. It's done by Southern Blasting and Coating. Southern Dustless Blasting and Coating by Eddie. He's been doing our powder coating for years now. But the way that the manufacturer has transported the decks to and from powder coat is they basically have the deck assembled. It sits on a trailer. It goes to powder coat. So one deck takes up roughly 16 square foot of that trailer. So now with this process, we still have to do one more shipping pallet that will stack on this one with the accessories. So we will go from so eight decks will take up 16 foot of the trailer, linear feet of the trailer. And then once we have this completely done, 8 decks will take up 8 linear feet of the trailer. So we're able to double our capacity to and from powder coat. So it just makes it a lot more efficient. But we weld it, do the cleanup, we stack them on these pallets, load them on the trailer, take them to powder coat, we powder coat them, put them back on these pallets, and we bring them in. So just trying to make things more efficient and less people touching them. So the less we touch these in the process, the quicker we can be, and it gives us more time to make sure everything's right instead of trying to be in a rush and throw stuff together. That's not how we want to do it. And right now we're still just learning all of the ways to make things better. By the end of the year, this thing will be running like a top. But yeah, so we've done this pallet for the back plates and the other pallets over there for the deck. So basically the back plates stack up like this, the deck stack up 8 on a pallet. Just like I say, just trying to make things more efficient. All right, so thank you for following along today, seeing the kind of the process and kind of where we are in the stage of doing all of our manufacturing in-house. I'd like to thank Trevor for everything that he's done for us throughout the years and for his time today. So thank you, sir.
Thank you for having me.
Absolutely. And obviously thank Nick for everything that he does. So yeah, Trevor, if you want to give everybody your information here.
So just give me a call or email. If you need any graphic services, SolidWorks, AutoCAD, CWI services, offer as well, so give me a shout.
Well, thank you guys. Hopefully you enjoy following along with our process of what we are doing. If you got any questions, let us know. If you got comments, let us know. If there's anything you see that we can do better, let me know. Because I am figuring out how it goes. Thank you guys. Bye.